Section 8.8 is Systems of Linear Equations. I can graph and solve systems of linear equations. A system of linear equations, or simply a linear system, consists of two or more linear equations with the same variables. A solution of a linear system in two variables is an ordered pair that's a solution of every equation in the system. A linear system has a solution at each point where the graphs of the equations intersect. So in example 1 here, I have two equations in my system. I'm going to graph each one of these and then see where they meet, if they meet at all. So here in my first one, I'm going to start at my y-intercept. Because it's y equals mx plus b, it's in slope-intercept form. Because my y is already by itself, I know it's in slope-intercept form. My intercept is my constant part, the one without a variable, and that's going to be where I start. So here I'm going to start at -4. My slope is the number in front of my x, my m value. And here it's a 2. And I write whole numbers and integers as fractions by writing them over 1. So I'm going to start from my y-intercept. Remember, our intercept's always on our y-axis. And I'm going to go up 2 for my rise over 1. Up 2 for my rise over 1. And I'm going to continue this pattern so that I have quite a few dots. Because when I connect these, I want it to be as close to accurate as I can get. I want it as close to a straight line through these points as I can get, because we're looking for where these two lines are going to meet. So I want it to be as close to the actual points that we can get so that I can get as close to the right solution once I have my intersection. My second line here is also y equals mx plus b. So here I'm going to start at 1 at my y-intercept. And my slope is -3. And remember, we write integers as over 1 to get our fraction. So instead of rising 3, I'm going to go down 3 over 1. Down 3 and over 1. Okay, I also can go up 3 and back 1 as long as I do both of my movements opposite. So instead of going down, I can go up. Instead of going right, I can go left. And again, we're going to connect those as close to being a straight line as we can. So you're going to want to use your straight edge, and you're going to want to extend that pattern there. And you're going to want to go through your graph, especially that first line, because we're not sure where the second one's going to meet it at. So we want to have a pretty good sized picture to go from. Here, where these two meet, that's my solution. So my solution here is the ordered pair of this point. X is 1, y is -2. So 1, -2. If I were to plug that into my equation, it would make both my top equation here, y equals 2x minus 4, and my bottom equation, y equals -3x plus 1, true. Okay, it's where they meet, and that's my solution. Again, we write it as an ordered pair. So again here, we're going to graph each of these equations the same way we've been doing all chapter. We're just going to do two on the same graph because they're the same system. They go together, and then where they meet is our solution. When the graphs of two linear equations have exactly one point of intersection, the resulting system has exactly one solution. It's also possible for a linear system to have no solution or infinitely many solutions. No solutions is going to be if we have parallel lines, because parallel lines never intersect. Infinitely many solutions are going to be if one of our lines is the exact same line as our second line. If they completely overlap, then it's going to be infinitely many solutions, because every point on one will also be a point at the second. So here in example 2, I'm going to graph each line. My top line here, I'm going to start at 1 because it's already solved for y. Y equals -2x plus 1. It's in slope-intercept form, and 1 is my intercept. And again, that's on my y-axis. My slope is the number that's being multiplied by my x, my coefficient. And remember, we write that as over 1 if it's not as a fraction. So I'm going to go down 2 over 1. My rise is -2, my run is 1. And again, we're going to extend that pattern so that we have an accurate line. And then we're going to take our straight edge and connect our dots. Arrows to show they continue. And there we go. Second line here, I'm going to start at 5 on my y-axis. It's my y-intercept. And my slope is -2 over 1. So I'm going to go down 2 over 1, down 2 over 1, and continue that pattern. And draw on our line. Now, if we look at our lines here, it doesn't look like they're ever going to cross. It looks like they're parallel. So here, my solution is no solution. Okay? Keep in mind that just because you didn't draw your lines long enough so they didn't cross doesn't mean that they won't. But if we look here, the change between our points is always the same. So here, from one point to the next on the same x is up 1, 2, 3, 4. Here, up 1, 2, 3, 4. Here, up 1, 2, 3, 4. So since I'm 4 away every time, they are parallel lines. We also could have seen that from our equations themselves. Remember, parallel lines have the same slope, but different intercepts. So since they have the same slope, we know these lines are parallel. We know that they're never going to meet, and there's no solution. No ordered pair will make both of these equations true. In example 3, we're going to solve the linear system. So here, my equations are not in slope-intercept form. Again, in order for them to be slope-intercept form, it needs to be y equals mx plus b. So here, since they're in standard form, I can either solve for y, I can use a table of values, or I can use intercepts. And I'm going to use intercepts. So here, to find my x-intercept, I'm going to plug a 0 in for y. Remember, when we cross our x-axis, our y value is always 0. So I'm going to have 2x equals -3. To get rid of my multiplication, I'm going to divide, and x equals -1.5. To find my y-intercept, I make x 0 because anytime I'm on my y-intercept, it means that my x value is 0. And don't forget that we take the sign in front of the number with it. So -y equals -3. And remember, if there's not a coefficient or a number in front of our variable, it's a 1. So now to get rid of my multiplication, I have to divide, and my y-intercept is at 3. We should label those as intercepts to help remember that they're points. So on my y-axis at 3, I have a point. Any 2 points I can connect with a straight edge. And we can extend that there. Arrows to show it continues. Now for my second equation, because I used intercepts in the first one and a little recap of that, I'm going to solve this one for y just to show you that path because we could have done that for both of these equations as well. So it doesn't matter. This is just another way. We could have done intercepts here again. Instead of to find my x, I plug a 0 in for y. To find my y, I plug a 0 in for x and solve like we did up top. But here I'm going to solve it for y and get it in slope-intercept form. So to get my y by itself, I first need to get rid of whatever doesn't have my y in it, and that's the 4x. I get rid of my minus 4x by adding 4x, and that's how I get it to be 0. Whatever I do to one side, though, I have to do to both. And remember, 4x has an x, 6 doesn't, so I cannot combine them. They're not the same type of things. Now, to get rid of my multiplication, I'm going to go ahead and divide by 2. And when I do that, I have to divide it to everything. We divide it to the right side entirely, which means we take it to each piece. And I get 2x plus 3. So now that it's solved for y, it's in slope-intercept form. My intercept is 3. My slope is 2. I'm going to start at my intercept. Again, b is where I begin. And I'm going to go up 2 over 1. Rise 2, run 1. Rise 2, 1 run. I can also do the same thing by going backwards for both. So I can go down 2, left 1. Down 2, left 1. And if we see, all of my points are on the same line here. So when I go to connect these dots, my line is going to be right on top of my yellow one. I'm going to leave them a little bit there so that we can see both lines. But essentially they're going to be the same line. And here that means that our solution is infinitely many solutions, because any ordered pair that makes one of my equations true will automatically work in my second one, because essentially they're the same line. Okay, they mean the same thing, they just look different. Feel free to pause here and give these a try if you'd like. We're going to solve the linear system by graphing. So in number 1, I have y equals 4x plus 2. Y equals x plus 2. So both of these, since they're y equals, tells me they're in slope-intercept form. In my first equation, I'm going to start at 2. And here my slope is 4, and I'm going to write that as 4 over 1. So I go up 4, right 1. Or I can do both of those things backwards. I can go down 4, left 1, as long as I do them both backwards. We can connect those dots with a straight edge. And arrows to show that the line continues. My second line, I'm going to start at 2. Here, remember, if there's not a number in front, it's a 1, and we can write that as 1 over 1. So I'm going to rise 1, run 1. Rise 1, run 1. Up 1, over 1. Up 1, over 1. And we'll connect those with our straight edge as well. Now, just because I graphed both lines doesn't mean I'm done. I'm looking to solve, which means I need to know what do my variables equal. Here, my x equals 0 and my y equals 2, because the point where they meet is right there. So x is 0, y is 2, and 0, 2 is my solution. Again, it's the one point that would make both of these true. It happens where they intersect. And I'm going to stop this here and finish the last couple examples in another video.